And welcome to this video. And today we will continue from our last lecture on Deutsch-Josiah algorithm, where we have seen the basics of what is the problem statement that we're trying to solve with that particular algorithm. And today's session will be about a simpler implementation of Joshua. So we have dropped the name of Joshua because Deutsch algorithm is basically a simpler implementation of that Joshua algorithm. And we will look into the details and the key aspects of what this algorithm does in order to provide us speed up. So to begin with, let's go back to the problem statement, what we had. Given two input, we were tasked with finding a function f such that the basis of the output from those two inputs, we can determine whether that particular function that we have applied on two inputs is a constant or balanced. We already saw the example in a binomial tree kind of structure where we have seen that to arrive at the conclusion of whether a function is a constant or balanced, classically, we will have to apply two queries with four steps. So that is, in a nutshell, how we can arrive at it. This is a simplistic example to give you the details about, or rather to prepare you with the details about how this can easily get complex in a much higher calculation uh, uh, complexity problem. So the simplistic view here is just for illustration purposes. Now, how should we conceptualize this algorithm? So let's assume that we have two qubits, x and y, and both are being placed in the superposition of 0 and 1. And then we're going to apply an oracle, the concept of oracle, as you already know, such that we're going to compute f of x, the function that we are aiming to find value of, which determines whether the function is constant or balanced on the x register. And then we evaluate the y register, which is an XOR of the register value and the fx, the function value that we are trying to determine. How should we manage the interference of that, or rather get the final value? We apply the Hadamard gate on the extract in one of the oracle cells, and that is where we're going to measure the final outcome. Now, the reason that we are starting y in 1, y register in 1 and not in 0 is to allow interference capability to kick in. By that capability, we mean we will also see that aspect of phase kickback, which is the core of this algorithm, will slide in when we start the Y register in the state of 1. So if we set this up, our initial state will look something is a superposition of 0 and 1. And then we're gonna apply the Hadamard gate on both the states. The calculation is simple. If you have doubt doing it or understanding it, you can go back to the quantum gates series or also to the quantum algebra series to see how this is being done. Now, as said, the y starts, the register y was starting at 1 because then the applying Hadamard on 1 will give you minus superposition. So it's a combination of state of 0 minus 1, where minus 1 represents a phase shift. This comes the Oracle definition because we have to pass this through an Oracle, which is nothing more than, without knowing the internal details of it, is an input which applies on an input pair and gives you an output. Now the Oracle has been represented by symbol U of F, and by U what it means is unitary to preserve the dimensionality. And if you want to know more about what is unitary, I highly suggest you to go back to the lecture of quantum algebra and quantum gates. While applying this oracle, what we see that the X register will remain unchanged and the Y register will receive the XOR of Y, the state of Y, plus plus what the function f of x is, something that we try to determine. Now, this will produce, after applying on the initial state the Hadamard gates, this will produce an superposition, and you can do this calculation on your own by hand, and you will see that a symbol of -1 with respect to the power of function is being pushed back. So the phase of x state is what we are trying to determine, because that will give us the final result of whether the function is constant or balanced. However, if you see in this calculation, -1 to that f of x function is what the y register is giving it back. And this is precisely what is called as a kickback, or the give up from Y register to X register. And this phase kickback is actually the key mechanism in Deutsch Joshua algorithm, which help you to determine the exact the exact state of register X. Now mathematically, the Y register is unentangled, so dropping this will have no harm at the end result, and that's why it can be easily discarded. Now, if you rearrange this equation around X register, you will end up with an equation, as you can see, and you can factor out the -1 raised to the power f of 0, because it's a global phase, it's unobservable, it's only there for the relative, it's unobservable, and what is important for us is that only the relative phase between the states is what matters. So the particular the particular output of -1 raised to the power f of 0 can be safely ignored. And then what we're going to do is what we have did always for inference, is that apply the Hadamard and then measure the output. So on the X register, if the function is constant, you apply the Hadamard and you will get the measured value is 0. And if the function is balanced, you apply the Hadamard, the function will turn out to be the 1. And then you measure these two values. This is the implementation of the circuit, very simple and straightforward. So not much of complexity here. And in summary, if you follow this step, that is where you will see how an exponential speed up has been achieved, where 2 queries were needed classically, and here it is a one pass of the one pass of the circuit that we have seen before will give you the output whether the function f is balanced or constant. So this is in a nutshell how the implementation of Deutsch algorithm works, which is, as I said, is a simpler implementation of Deutsch Joshua. But the important concept to take from here is that phase kickback part, which the register Y gives it to X, which in turn help to determine during the interference where f of x is either a constant or a balanced function. Now you increase the number of outputs from 2 to 200 or 200 million, and you will see how this speed up actually plays a very important part in your overall calculation. So with this, I'll stop here. Thanks for listening, and I'll hope to see you in the next session.